With that, it's my pleasure to introduce Ayush Sekhari today. He is currently a postdoc with Stochastic at MIT. Before that, he did his PhD at Cornell with Kadrik Sidran and Robert Kleinberg. And Ayush is working on different topics in optimization, online learning, reinforcement learning, control, and he's very much into theory. So today we're going to hear about adversarial decision making. Ayush, looking forward to your talk.
Great, thanks, Johannes. So I think before I start, I should give a warning. So I'm currently in India, and there's a very small probability that there will be a power cut, and I will like completely lose the Wi-Fi power and everything. So if I vanish while speaking, like you know why that happened. And generally, it comes back in 2 minutes or something. So just wait for 2 minutes. If I don't show up, then that means it's a bigger cut. Okay,
At,
so. Mhm.
at least we have the slides. We can start with the slides.
Yeah. I think I shared the slides already. Cool. So thanks for inviting me. This is some joint work with Dylan Foster, Sasha Racklin, and Karthik Sridharan. Please stop me whenever you have any questions, confusions, anything. I think my goal is to make this talk as interactive as possible, but hopefully not adversarial. So I don't think I need to tell this audience that over the past decade, there has been an emergence of a variety of problems where an agent is learning by interacting with some environment. For example, starting from the simplest problem of finite armed bandits to more complex problems like inventory management, self-driving car, games, robotics, and so on. All of these problems come under the framework of interactive learning or decision making. However, as these applications are getting advanced, one important uh, uh, factor to take into consideration is that one cannot assume that the underlying environment that the agent is interacting with is stationary. In the sense, the underlying environment can itself change over time. For example, in the case of inventory management, the supply, demand, and production can change depending on the time of the year, whether it's a festive season and so on. Or for example, in the case of self-driving car, the environment can change depending on weather, time of the day, and so on. So the focus of this talk is to consider interactive decision-making problems where the environment can change over time. Towards that end, here is the itinerary for the talk. So I'll first start by giving the setup of adversarial decision making and provide illustrations showing the generality of this framework. Then I will go into some prior work in stochastic setting, and then eventually go into the new results for the adversarial setting. First discussing the lower bound proof, then providing the algorithm, finally some proof sketch for the upper bound, and then we will conclude with some discussion of like semi-technical discussion. So let me start by introducing the adversarial decision-making setting. This setting comprises of a nature, which acts as an adversary, and a learner. The nature is assumed to be equipped with a model class script M that the learner knows, and the learner has a decision space, a policy class pi that the nature knows. The interaction between the nature and the learner goes over T rounds, where at the beginning of every round, the nature chooses a model MT from the model class script M, and the learner chooses a distribution PT over its decision space or policy class. Then after making these decisions, the learner samples a policy pi t from PT and plays it against the nature and gets back some reward and observations drawn by interacting the policy pi t on the model MT. In particular, we consider the partial feedback setting where the learner only gets feedback corresponding to the policy's pi t that it plays and not any other policy in the policy class. The performance of the learner is measured by its regret, which is defined as follows. Given a sequence of model M1 to MT, the regret is defined as the difference between the expected cumulative reward of the best policy in the policy class versus the expected cumulative reward of the distributions PTs that are chosen by the learner. Just a notational point, throughout the slides, we will use the notation f to the power of m pi to denote the expected reward for the policy pi on the model M. The goal of this work is to understand the min-max regret, which is defined as the worst-case regret for the worst-case choice of the sequence of models M1 to MT that can be chosen adaptively and adversarially depending on the learner's actions in the past. Any questions so far on the setup?
Just a quick question. Your policy space, big pi, is it, or stochastic policy is included, or is it just deterministic?
It can be stochastic or deterministic. However, most of the examples that I will discuss will consider deterministic policies, except for the MDP setting. But you will see as I give illustrations that it doesn't really matter whether they're stochastic or deterministic.
Maybe just to clarify, so when you say min-max regret, you mean like there's a min or infimum over all policies, so it's the optimal policy.
Yes. Okay, so let me, before I go into all the technical results, let me first give some examples motivating this framework and hopefully to convince you the generality of this adversarial decision-making framework. So let us start by looking at the simplest example that I'm sure many of us in the audience have like dealt with in the past. So this is the simplest adversarial multi-armed bandit setting. Over here, the policy class or the decision space of the learner simply denotes arms 1 to A, which are also called actions. And the model class of the nature denotes all sub-Gaussian reward distributions. Now, when the learner plays a policy pi t against the model MT, it gets a reward RT, which, for example, could be drawn from a Gaussian distribution centered at the mean corresponding to that policy pi t on the underlying model MT, or it could be deterministically chosen to be the mean, which is f of MT pi t. And here, the observation that the learner gets is precisely the reward that is sampled from the underlying model. Now, this framework is rich enough to capture more complex bandit-like problems. For example, starting with the bandit linear optimization problem or linear bandits, where instead of having discrete arms, we can have a continuous decision space or policy space. For example, the policy space could be vectors in RD, and the model class could consist of models whose expected mean is a linear function over this policy class. Now, every time you play a policy or a vector in RD, you get back a reward RT corresponding to a noisy sample on the linear function f of MT by t. And again, here the observation is precisely the reward. And then we can keep on generalizing it. For example, this also captures bandit convex optimization problem, where now the model class consists of functions whose expected mean is convex with respect to the policy pi. And furthermore, this also includes non-parametric bandits, where the expected mean is just assumed to be Lipschitz with respect to the underlying policy class. Now, so far I have discussed examples of bandit-like problems or bandit problems where the observation only consists of the rewards. However, just to give an example, we can also incorporate more complex problems where the observations are richer. The classical example here is that of adversarially changing Markov decision processes. In particular, we consider finite horizon episodic MDPs, where a model in this family is parameterized by 6 items, consisting of a horizon H, a state space S, an action space A, an initial distribution B1, a reward kernel R that maps states and actions to stochastic rewards, and a probability transition kernel P that maps states and actions to distributions over the next states. Just to explain our framework better, we look at how the adversarial decision-making framework captures adversarially changing MDPs. In particular, in our framework, the decision space of policy class now consists of a set of policies over the underlying state space. The model class is just a family of episodic MDPs with horizon H. And in the interaction between the learner and the nature, whenever the learner plays a policy pi t against the model MT or an MDP MT, the learner gets back two observations. The first is the trajectory S1, A1, R1, S2, A2, R2 to SHH, RH, drawn by interacting the policy pi t on the MDP MT, and a cumulative reward RT, which it suffers in this episode. And finally, just as a small comment, we do not necessarily need to restrict ourselves to partial information problems. The framework also easily captures full information problems like learning with expert feedback, where on every query, you get back observation corresponding to all the decisions or all the policies in your policy class. Any questions so far on these illustrative examples?
So I have one.
Mm-hmm.
So is this really the standard model, like the standard adversarial model? Because you're also adding noise to the observation. As far as I know, like the adversarial model, you would just see that there's no noise in.
Yeah. So let me go back a few slides where this is the multi-arm bandit.
Mm-hmm.
So it actually captures both of these models where if you want, you can add noise or you cannot add noise. So for example, if you look at the second bullet, there the reward is deterministic corresponding to the underlying like multi-arm bandit losses that you choose for the round. Okay, so far, all of these examples, like there's nothing, these are not new examples. They have been well studied. There's a long line of work on each of them independently. However, the main goal of this talk is to develop a general framework for interactive decision-making in adversarially changing environments. In particular, we want to understand how does the min-max regret depend on the model class M that we are interacting with in this adversarial decision-making setting. Now, before I tell you the results for the adversarial setting, let me first take a step back and connect these results with a prior work on stochastic setting. In the stochastic setting, it's a similar interactive model between a learner and an adversary. However, we assume that the adversary's model MT does not change over time. So it's a stochastic nature. So we assume that the MT is fixed to be M star for all times T from 1 to T throughout the interaction. So this setting was previously studied in a very popular paper called The Statistical Complexity of Interactive Decision-Making, where they tried to provide a characterization of the statistical complexity of interactive decision-making in the stochastic setting. And along with a few future works, they essentially were able to get matching upper and lower bounds on the min-max regret up to log factors. And in order to get these matching upper and lower bounds on the min-max regret, they introduced a new complexity measure called decision estimation coefficient. And they show that decision estimation coefficient characterizes regret in the stochastic setting. Our primary contribution in this work is to show that the decision estimation coefficient also characterizes the min-max regret in the adversarial setting, but with a slight twist, which will become clear as I go through the main results. Now, let me delve a bit into what this quantity decision estimation coefficient is. This quantity decision estimation coefficient was introduced in this prior work and is defined as follows. For a model class strip M, decision space pi, and some reference model M bar in this class strip M, and some scale parameter gamma greater than 0, the decision estimation coefficient is defined as follows. Just pay a bit attention here because this will be an important quantity that will come again and again throughout the talk. So I think like it's useful to delve a bit into what this quantity is. So the decision estimation coefficient of a class script M with respect to reference model M bar and a scale parameter gamma is the value of a min-max problem. where the min player chooses a distribution over the decision space and the max player chooses a model over the model class. And both are trying to optimize with respect to this objective that at a high level provides a balance between the worst case regret and the information that is gained by playing decisions according to P, the distribution P. Just to clarify the notation, throughout the talk, we will use pi star m as the optimal policy or the optimal decision corresponding to a model M. And this quantity D Hell square is the Hellinger divergence, which is used to capture distance between distributions and is defined as shown. So the decision estimation coefficient for a model class M is defined as the soup over this quantity shown above with respect to all reference models M bar in the class M. Any questions here in terms of definition of this quantity? Okay, so now let me go forward and show you what we know for the stochastic setting. So in the stochastic setting, these prior works showed that the expected regret given a model class script M is upper bounded in terms of an optimal trade-off for the scale parameter gamma of the decision estimation coefficient of model of script M at the scale gamma times t plus gamma log M. At the same time, they showed that this kind of dependence on decision estimation coefficient t and gamma is actually also necessary for the min-max regret by providing a lower bound. So the expected regret is lower bounded by the best trade-off for the scale parameter gamma, min between the decision estimation coefficient of the class script M times t and gamma. And just to remark, this is an informal result. The precise lower bound as presented in the first paper was scaled with a localized version of DEC, and there were some gaps in high probability versus expected regret bounds, which was fixed later by this newer work called tight guarantees for interactive decision making with decision estimation coefficient. So as it stands, we have almost matching upper and lower bounds on the expected regret. And one can say that the decision estimation coefficient of a class script M characterizes the min-max regret in the stochastic setting for decision making with respect to script M. Because this is a heavy theorem, before I go into our results, let me first give an example and show you how to interpret these quantities. Let's go back to the simplest example of multi-arm bandit, where the decision space consisted of arms 1 to A, the model class consisted of sub-Gaussian. So here we'll just consider Gaussian distributions with means FM, and the observation just consists of rewards. For this problem, for any reference model M bar, the decision estimation coefficient for this model class script M with respect to M bar is as follows. This is just copying the definition from 2 slides before. Note that this has a dependence on this Hellinger divergence between M pi and M bar pi. But notice that all we get by interacting the model and the policy pi in this case is an observation, which includes a reward drawn from a Gaussian distribution with mean of Fn pi and variance 1. So substituting this property over here, we can replace this Hellinger divergence by the square loss between expected, the square distance between expected means. And by explicitly solving this min-match problem, one can show that for this particular problem setting, the decision estimation coefficient scales something like A over gamma up to constants. So plugging this into the lower bound that we presented in the previous slide, we immediately get that the expected regret is lower bounded by square root of AT. And at the same time, plugging this form of decision estimation coefficient in the upper bound, we get that the expected regret is upper bounded by square root of AD log size of M. So the upper and lower bounds match up to this log M factor. And the lower bound is actually tight for this problem. Okay, any questions so far before I go into new results?
We do have one question in the chat.
Mhm.
So the question is by Vanchai, why can we not use the conventional complexity measure like current number or the VC dimension? So what's the advantage of using the decision estimation coefficient?
Right. So I think like all of these quantities could be relevant when trying to deal with this log m dependence. You can try to think of like replacing them by appropriate covering numbers. But the essence of decision estimation coefficient comes in order to capture the price of exploration. So in some sense, like this captures how much how to optimally trade off between exploration and exploitation with respect to the underlying model class that you're dealing with. So it's a new complexity measure. I hope that answers your question.
And sorry, just to clarify, in these results you're showing, is calligraphic M always assumed to be finite?
Mm-hmm.
Yeah.
So you can assume that we always replace M by like a covering of M at an appropriate scale. And the hope is like at least like right now, assume that this is not like we can construct problems where this log M is problematic, but like yeah. So throughout the talk, we'll assume that log M is not T dependent at least.
And I think there was another question in the chat asking in this case exactly what log M was. This specific example.
Oh, I see. So for example, for the multi-M bandit problem, you can just consider a complete discretization of 0, 1 to A cube. So then log M would be like poly A, log 1 epsilon in that case. Where epsilon is a discretization parameter.
Thanks.
Thanks. Cool. So now, after giving you a summary of what we know from the stochastic setting, introducing this new complexity measure called decision estimation coefficient, giving some examples and so on, let us finally go into the actual new results in the talk. So the new results, as I mentioned earlier, this work is about the adversarial decision-making setting, where we assume that the model MT may change with time in an adversarial and adaptive manner. So what is the characterization of the min-max regret in this setting? So in our work, we provide a similar result to the stochastic setting. In particular, we provide a new upper bound and an algorithm that for any model class script M, policy class phi, and scale parameter gamma, ensures that the expected regret is bounded by the decision estimation coefficient, but of the convex hull of the model class times t plus gamma log phi. At the same time, we show that this dependence on the decision estimation coefficient of convex hull of M is real by providing a lower bound. In particular, we show that for any model class M, policy class phi, and scale parameter gamma, there exists an oblivious adversary for which the expected regret is greater than the min between DEC of gamma convex hull of M times T and gamma. And again, here as well, the precise lower bound scales with a localized version of DEC, and we can use machinery from some later papers to get tight upper and lower bounds for the expected regret. So just to put the two results in comparison, so for the stochastic setting, the expected regret behaves like DEC of gamma times M times T plus gamma log M. Whereas for the adversarial setting, the expected regret behaves as DEC of convex hull of the model class M times T plus gamma log phi. And for now, for comparison, assume that for the adversarial setting, the policy class or the decision space pi that we choose is just the set of greedy policies corresponding to the models in the model class. So the gap between log M and log pi could be ignored. And in that case, the price of adversarially changing environment is precisely governed by how this complexity measure decision estimation coefficient changes with the convexification of the model class. And in some problems, the price of this convexification is mild. On the other hand, for some problems, the price of this convexification could be significant. For example, if you consider simple bandit problems like multi-am bandit, linear bandits, even convex bandits, over there, the DEC for the model class is the same as the DEC of the convex hull of the model class. And this immediately tells us that the min-max regret in the stochastic setting and adversarial setting are equivalent to each other up to the discrepancy between log m versus log pi. Whereas for some other setting, for example, episodic tabular MDPs, the gap between the DEC of M and DEC of convex hull of M could be significant, where the DEC of M scales polynomially with all problem parameters, whereas the DEC of the convex hull of M scales exponentially with the horizon and S. But the key takeaway from this talk, if you have to take away like one sentence, is that the gap between the min-max regret and the in the stochastic versus adversarial setting is precisely how DEC behaves under convexification. Okay, any questions so far? Because I did give some heavy new things.
Can you maybe say what is the complex combination of two models?
Yeah, so I think it will become clear maybe like 2 slides from now.
Mm-hmm.
Think of it as a mixture distribution between the two models.
Randomness when you take convex combinations.
Okay, maybe let's come to this question in 2 slides. Is there any other question regarding the results or examples or definitions? Okay, so let me go forward, and hopefully the next slide will also clarify the previous question from Johannes. So I'll first look into the proof sketch for the lower bound and show where the convex hull of M is coming from in the adversarial setting. In particular, I will provide a very high-level sketch for how we expect, why we expect that the expected regret in adversarial setting is scaling with the DEC of the convex hull of the model class. So this proof sketch will be based on the argument that we know that in the stochastic setting, given the model class, the expected regret depends on the DEC of that model class times T and gamma. So the proof will construct an adversary and invoke this result for the stochastic setting. In particular, in the adversarial setting, consider the following adversary, which is parameterized by a distribution mu star over the model class, such that at every round, the adversary simply samples a model MT independently from the same distribution mu star and gives the feedback to the learner corresponding to this sample MT. Now, one can think of this model MT as, so one can think of this adversary as a fixed model M mu star, which just plays distributions over the model class. So this shows that the adversarial setting is at least as hard as the stochastic setting, where one can lift the model class to consider all models M mu corresponding to distributions mu over the model class, which is precisely the convex hull of the model class. So does this clarify your question, Johannes?
Yeah, I think so. So if you have two models with, say, one reward 0 and the other is 10, then you would, in the convex combination, you would see noise between the two, like a randomization between.
Yeah. So if you weigh them half and half, with probably half you draw the first model, and with probably half you draw the second model. Okay, so now let's move on to the upper bound. But before I go into the proof for the upper bound, let me go into the algorithm that attains that upper bound. So the next section will go into discussing the algorithm that achieves the upper bound and the regret. One thing to note is we provide an algorithm that actually obtains the regret upper bound with high probability. So just keep that in mind, and I'll recap this point when it comes back. Okay, so before I go into the upper bound algorithm, I do have some acknowledgements to make. So this algorithm is actually highly motivated by two very interesting works. So there is this work called Exploration to Optimization in Partial Monitoring by Chaba and Tor. and a follow-up called mirror descent and information ratio by Tor and Andreas. So as you will see, the algorithm is heavily based on this idea of exploration by optimization. And in fact, what we do is we provide an optimal way of doing exploration by optimization to obtain a high probability regret guarantee that can also work for adaptive adversaries. Okay. So the key insights about the algorithm. So first, let me mention what are the key challenges that algorithm needs to address. So the key challenges is a combination of two things. The first is partial feedback, as a learner only observes feedback corresponding to the policies that it plays. And second is this adversarially or adaptively changing environment, which the learner has no control over. At a high level, the aspect of partial feedback is handled by constructing rewards estimators and somehow reducing the problem from a partial information problem to a full information problem that we know how to solve. And this is precisely where we use exploration by optimization machinery to come up with the right way to reduce a partial information problem to a full information problem. And what we will show is that our provided algorithm has actually regret guarantees in high probability that accounts for adaptively changing adversary. Okay. So before actually going to the full-fledged algorithm, I want to start with some motivation on where these ideas are coming from and go over some very elementary algorithms and see how these intuitions can be used for the general adversarial decision-making framework. So let us start by looking back at the simplest problem that we discussed before, that is learning with expert advice. So we start by looking at the full information problem, which is you're given A actions, and on every round you play a action pi t from the space, and you get a reward RT pi t, and at the same time you observe a reward corresponding to every action in this class. Now this problem has been super well studied, and there are many popular algorithms. One popular algorithm is exponential weights algorithm. This is a very simple algorithm. It is an online algorithm. At every round, it computes a distribution QT over the action space by looking at the history of past rewards corresponding to different policies. So the weight that is given to a policy pi is proportional to the exponential of the cumulative reward observed by that policy divided by the scale parameter gamma. And at every round, the policy that the learner chooses is sampled from this distribution, and you get a full information feedback. Now, this algorithm is known to be optimal in the expert advice setting. In particular, one can show that for any scale parameter gamma that goes into the step size of this algorithm, this algorithm guarantees that the expected regret is bounded by t over gamma plus gamma log a, which by optimally choosing gamma leads to square root of t log gamma. So this full information setting is super well understood. But recall that the adversarial decision-making setting that I introduced earlier is that of partial information. So let us see what is the partial information version over here to get some motivation on how to think about algorithms. And a simple partial observation extension of this is that of multi-arm bandit, where when you play a policy or action pi t, you only get to observe the reward corresponding to pi t. Now, this is also a super well-studied problem. I'm not talking about new algorithms here, but just trying to make connections to give intuition on how we will think for general algorithms. Now, the algorithm that solves this problem is EXP3 algorithm, which is a simple extension of the experts algorithm that I discussed earlier. Here, again, we compute a distribution QT over the decision space. And then every round, sample the policy or to play right now using the distribution QT that we computed. But because we only get a partial feedback corresponding to the action that we played, we construct a reward estimator, which we denote by f hat pi, as shown in the slide, that is plugged back into the exponential weights algorithm and so on. So the key idea of this EXP3 algorithm is it solves the partial information problem by appealing to a full information problem by constructing appropriate reward estimators f hat. So in the case of bandit, this is what is called as inverse propensity weighting estimators. And again, for the bandits, this particular algorithm has a regret bound that scales with AT over gamma plus gamma log A, and by optimally tuning the scale parameter gamma or step size given by gamma, you get a regret which is AT log A, which is almost optimal for this problem. And while this particular algorithm gives you regret in expectation, you can slightly modify the action distribution that is chosen by the full information algorithm or the exponential weights algorithm and get a result that holds with high probability. But the key insight to take away is that we essentially solved a partial information problem by reducing for a full information problem by using appropriate reward estimators and modifications of the distributions QTs that are proposed by the full information algorithm. And this is precisely the idea that we will extend to the adversarial decision-making setting. In particular, we will solve the partial information problem by coupling it with an appropriate full information problem, where the sequence of operations will go as follows. So at every round T, the full information problem will come up with a proposal distribution QT over the decision space pi. Oh, before I go further, I should remark that the partial information problem is what we are actually solving, and full information problem is what we are simulating. So the full information problem comes up with a distribution QT over the decision space pi, and then chooses a policy pi t prime from QT. But looking at the proposal QT corresponding to the full information problem, the partial information problem will construct a distribution PT depending on what QT was proposed. And the learner in the partial information problem will play PT. At the same time, the nature will choose and model MT adversarially. The learner will choose a policy pi t from this PT and play it against the nature and get back some partial information corresponding to the policy pi t that it plays. So the important thing is the learner in the partial information game only gets information corresponding to the policy that it played. But depending on the observations and rewards that the learner got, it will construct a model or a loss estimate, a reward estimator in the full information game, which the learner will observe. So the learner will get a reward corresponding to every policy or every decision pi in its own class. So in this way, we will try to connect the partial information game with the full information game and eventually solve a partial information game by relying on an algorithm for full information game that we know has some good regret properties. In particular, you can think of the two problems independently as trying to do corresponding regret minimizations, where the partial information game minimizes regret with respect to expected rewards ft, and the full information game minimizes regret with respect to expected rewards f at t, which are constructed by the partial information game. Okay, so any question at a high level on this sketch before I go into the algorithm?
I might have missed this, sorry. What's the relationship between QT and PT?
So it will become clear in the next slide, but the idea is like instead of directly using the proposal distribution QT, the learner in the partial information game decided to modify it. And like
QT, or not,
yeah,
we'll show... QT, I guess it's constructing it. Yeah. It will use QT to pick PT.
It will use QT to pick PT, exactly.
Okay. Brilliant. Thanks.
Okay, so now let me flash the algorithm. This will contain some big equations, but they are very simple. And the intuition is essentially this. So the algorithm consists of three main steps. Okay, so the first step is, this is the full information problem that proposes a distribution QT. And all it does is running an exponential weights update using the estimators f hat 1 to f hat t minus 1 that are generated in the algorithm and will become clear in step 2 and step 3. So the full information game proposes a distribution QT by running exponential weights on f hats that are constructed from the past rounds. Now, once you receive QT, in order to solve the partial information problem, you solve a min-max problem that is parameterized by Qt and gamma. So this min-max problem has the following structure. So the min player chooses a distribution P over the policy class pi. This is the new PT that it uses to actually take its decisions. And at the same time, it chooses a function G. The mapping of the function G is G maps a policy cross observation to some real to 0, 1. Okay, so in order to solve the partial information problem, given a Qt, we solve a min-max problem in order to get a PT and GT. We sample a decision corresponding to PT, get an observation by interacting with the nature. This is the part where we only get the partial information. In particular, we only get MT pi t. And by using the partial information OT, we form a reward estimator FT by doing some inverse propensity weighting with respect to these functions GT that we solved in step 2. So the algorithm is very simple, 3-step procedure. In step 1, you're appealing to a full information algorithm, essentially exponential weights. Then you're looking at the output of exponential weights, plugging it into a per step min-max problem, solving the min-max problem to get to know what to play and a function GT. And using the observation that you get from playing a decision from PT, you compute a reward estimator F hat using GT and this observation, and plug that back into the exponential weights mechanism. Now, the next slide, I will just flash what this optimization, per step optimization problem gamma is. In particular, this gamma has a big expression. This gamma is as follows, but it's simple to interpret. The gamma contains of 2 parts at a high level. The first part corresponds to worst case per step regret. And the second part ensures that the functions G that we are dealing with had good tail behaviors on the reward estimates. And as we mentioned before, this expression is parameterized by Q and gamma. And at every round, we plug in the Qt to solve this min-max problem and get a PT and GT. So the key contribution of our work was to come up with this optimization, this per step min-max optimization problem, and show that this can provide high probability regret guarantees that can handle adversarial, adaptive adversaries. Any questions so far before I go into further details on how the proof works? So again, like this is all based on this exploration by optimization line of work by Chavatar and others.
So maybe you're gonna say this later, but how is this related to the DEC?
Yeah, that's gonna be like that's gonna come. Yeah.
Okay.
Good question, because like so far I've not talked about DEC at all, right? Like this is just a optimization problem, and yeah, like you will expect to depend on the, like in some sense, the max value of this optimization problem in the regret upper bound, which it will, and I'll show why it is related to DEC.
Mm-hmm. But then also,
but at least, like, are there any questions at the level of algorithm, like what's going on?
Are you going to talk about the differences to our work, like the details of like the different choices made here versus there?
Not really.
Because like I think that that's the curious question.
I think like the one main difference is this like high probability argument. Like
right.
We try to.
But is there a claim that the previous choices wouldn't give you that?
No.
We just don't know.
I don't know.
Yeah. Awesome. And there was a difference in terms of, at least in the first work, we had slightly more general way of constructing estimators.
Right.
So here you just choose the inverse propensity. Is there any loss there, or?
So at a high level, like because this gives you the min-max optimal, at the min-max sense, there's no loss.
Okay.
But like if your objective is something else, like
Maybe refined compared to
right,
that.
exactly, there might be some other version.
Okay. Yeah. Cool. Thanks.
Yeah, but like I should say, like I really like the idea of like just it's very beautiful to have like this put an estimator and then solve the min-max problem, and that's the complexity in some sense. So I think the main contribution that kind of like solidifies this particular effort is to show that exploration by optimization objective is actually related to like DEC, and as I will show later, also related to information ratio. So that kind of shows like it's the right thing if we care about like min-max of it. I hope that makes sense.
Sure.
Okay, so now let me go into the proof. The proof is very simple, and you'll see where all these big terms are emerging as soon as I show you the proof. So I'll essentially provide the following proof that that with probability at least 1 minus delta, the regret is bounded by DEC of convex LFN times T plus gamma log pi over delta. And just to recall, this regret is the gap between the best policy with respect to the cumulative expected reward versus the total reward of the learner. Okay, so this is again a proof sketch. So one thing we'll do is we'll simplify and remove these expectations and just denote this notation STPT to denote expected value of FT of pi with respect to draws from PT. Okay, so the first idea is we want to bound this regret. So let's just add and subtract the regret corresponding to this full information game, or estimate as F hat. Okay, now notice that the second term over here is precisely the regret for the full information problem. And using the standard analysis for exponential weights, this can be upper bounded as follows. This is a very standard expansion for the regret corresponding to exponential weights. But okay, so now we have all these, a lot of terms. What you can do is using some standard concentration by using the fact that we are drawing policies corresponding to PTs and like the definition of FT, using a variational form of KL and so on, you can show that this is upper bounded by the following expression. And notice that the first term is essentially what we use in the definition of this per step min-max relation. Essentially, this is the value of that per step min-max optimization problem with PT, GT, and pi star MT plugged in. So now moving forward, I'll hide this big expression and just call this as this gamma. Now we don't know what pi star and MT is. So what we can do is we can just remove the explicit dependence of pi star and MT by taking a max over all pi in the policy class and M in the model class. But notice that now PT and GT is precisely the value of the argmin corresponding to this min-max optimization problem. So we can do this for free, where we can replace the dependence on PT and GT by this min over P and G. And recall that this is exactly what we used in the step 2 of the algorithm. So moving forward, we just call it exploration by optimization objective, EXO, at the scale gamma of the model class M and QT. You can notice that this quantity only depends on gamma, QT, and script M, and nothing else. So just plugging this form in, we get that the expected regret is bounded by sum over T from 1 to T of this exploration by optimization objective at QT. And again, we can just remove the dependence on QT by taking a, so now this is the complexity analysis as to what's the min-max complexity. So we can affirm this by taking a max over all QT. So this becomes max Q exploration optimization gamma script MQ times T plus gamma log pi by delta. And the key technical lemma in the proof is to show that this max exploration by optimization of script M is exactly the DEC of convex LFN. So once you plug that in, you get the desired upper bound that the expected regret, or this actually holds with hyperbole, is upper bounded by DEC of convex L of n times D plus gamma of pi by delta. Okay, so before I conclude the proof sketch, I think all of you might have this question. Okay, like I think I did most of the steps as natural upper bounds and so on, and suddenly I flashed this technical lemma that the actual thing that we have in the upper bound is precisely DEC. So I'll give some intuition as to why the regret is upper bounded by DEC of convex L of model class. In particular, I will show why this max Q is equivalent to DEC of convex L. And essentially what I'll give intuition to is where this convex L is coming from and where Hellinger divergence is coming from, and hide a lot of algebra from the slides. So first of all, the convex L essentially appears through a min-max duality. In a sense, we want to get an upper bound on this max Q exploration by optimization of script M with respect to Q. Let's just look at what it is. It's this quantity, max Q, min P, G, max pi P, and so on, where gamma is the per step min-max objective used in the algorithm. Now, I'll not prove this here, but just believe me that this objective is actually convex in P and Q, but it's not concave in pi and M. So in order to do anything with this quantity, we need to convexify over pi and M space. And this gives a joint distribution over the model class and decision space, denoted by mu. And now this becomes a convex concave objective, and you can do a swap. And essentially what happens is after doing the swap, this entire min PG and so on, like all the terms following min PG, they essentially simplify to a DEC term. But because of this min-max swap and the fact that we had to look at joint distributions over M and pi, now we have to suffer from the fact that we have to look at models that are mixture models over the model class, and that's why a convex L appears in the upper bound. Okay, so now let me go a bit deeper into what is going on here and like show you why this expression that I hid under this orange block corresponds to something like a DEC. In particular, I will show where a Hellinger divergence appears from when getting this upper bound. And again, this is at a very high level sketch. The Hellinger divergence essentially appears from a variational formulation of Hellinger divergence. In particular, we have that for any distributions P and Q, up to constants, the Hellinger divergence is given by the supremum over function of 1 minus the product of moment generating functions corresponding to P and Q of e to the G and e to the minus G respectively. So what happens is if you look at the expression that we discussed in the previous slide, this big exploration by optimization objective, and after doing this min-max swap, this is what the expression looks like. But now you can notice that we get some familiar terms corresponding to the variational formulation that I showed above. In particular, after rearranging the terms and computing the corresponding priors and posteriors, we can show that this is essentially, it's actually exactly like we get a term that looks exactly like what we have in the above variational form. And by invoking this result, we get that we get a Hellinger divergence over here. So now you can see something that looks very similar to the definition of DEC that I showed in the beginning of the talk. And using some further algebra, you can show that this is upper bounded by the DEC of the convex hull. So I hope this gives some intuition on where the Hellinger divergence comes from and where the convex hull of the model class comes from. So I think I'm closer to the end of the talk. I will just conclude by mentioning one last thing. So this problem of trying to come up with general measures of complexity for solving decision-making problems or bandit problems is not new. We already have some prior works. And one popular prior work is that of information ratio. So what we show in this work is a new variant of information ratio. It's not a new variant. We look at this notion called as parameterized information ratio, which I think was introduced by Latimore and Kyorgi in 2021. And what we essentially show is that this information ratio is equivalent to the exploration by optimization objective, which is equivalent to the DEC up to constants in the scale parameter gamma. So any of these quantities could be thought of as the right complexity corresponding to adversarial decision making. But the choice of DEC is interesting because it puts it in a very interesting contrast with the stochastic setting, and the fact that the gap between the stochastic and adversarial is exactly convexification. Cool. So I'll finally conclude and provide a summary of what we discussed today. So in this work, we provide a characterization of the min-max regret and adversarial interactive decision making, and we show that the difference between the stochastic and adversarial setting is precisely how DEC changes with convexification. And in order to obtain these results, we provide an algorithm that is high probability bounds and operates by reducing from a full information problem by using exploration by optimization technique introduced in prior works. And finally, in the paper, we have a lot of new techniques which could be interesting. So I recommend people to take a look. And in particular, we show an equivalence between information ratio, DEC, and exploration by optimization, which could also be of independent interest. Good. Thank you. That's it. So now I can take as many questions.
Yeah, thank you, Ayush. Awesome.
Mm-hmm.
Yeah, we'll take some questions.
I'll show the proof sketch. There might be some questions there.
Yes, I think I'm still trying to digest it a bit.
Mm-hmm.
So I had one question in the proof. Are you
Okay.
convexifying over pi?
Yeah, that
So what's
separates.
the yes? So what's the intuition on this, and like why is the adversary choosing decisions? That seems I don't see
So,
why.
so the thing is like, this is basically denoting the optimal policy that's adversary. Like this pi is the optimal policy. So adversary chooses a model, and you can assume that the optimal policy that you care about is the one induced by the model. So this pi is not the policy that the learner plays. It's
Right.
corresponding to the it's corresponding to the pi star that you have in the regret, basically. This pi star.
But why is there this convexification over all actions or policies pi and not just the optimal action for?
No. So in the proof, we actually use that, like we simplify this, and that's why in the end you only get like a DEC of the convex LFM. Yeah, I just like
and
didn't want to separate it.
It's not the optimal action of the model because over multiple rounds this could be a different action.
Yes, exactly.
But you should at least restrict it to like Pareto actions that can be optimal. So if you have a model class where some action is always optimal, would that matter?
No, I think that you should always do like anyways, given a model class and a decision space, you should throw away all the decisions that.
Well, not for information.
True, sorry. Yeah. Yeah, it's not clear.
But yeah, so the role of the pi is the optimal action here. So that's why it appears in the max and the convexification.
So in a sense, like, let us look back at where this gamma term is coming from. Essentially, like when you do all the concentration and all that, you get this min-max objective with respect to pi star and empty, where you don't know both pi star and empty. So you take a max over both of them.
But again, I could ask the same question. So why is the maximum over pi star not restricted? But that even applies to previous work, maybe. Not sure.
I think like maybe, okay, I don't know if that will satisfy you, but maybe a good way is like it's not necessary that in the adversarial setting, the maximizer corresponding to the cumulative sum is a maximizer corresponding to some model, right? So this pi star could be not on the like Pareto optimal in the way you defined it. Does that so this probably does not happen in the stochastic setting, right? Because all of these correspond to the same model. So then this cumulative of ft of pi star is same as f of m pi star, where m is a fixed model. Then the adversary chooses it every round. So then you can just consider the optimal policies.
But going back to a step where you're bounding the pi star m in gamma by the maximum, you were doing that for each t individually, even though pi star we know is the best in hindsight. There's nothing we can. I mean, we don't lose anything clearly by doing it this way. But that's a bit surprising, I guess. We don't need to consider the whole round. And what was the next step? Sorry, I've forgotten already.
Oh, so next step is like once you put a max over here, you realize that in the algorithm, the PT and GT that you play is exactly corresponding to the min over here. So you get a min max. So this step is actually an inequality. It should not be an inequality over here.
Yeah.
Can you say again what G exactly is? So G is an estimator, but
right. So G has the following signature. It does the following. If you look at the form of f hat, that might become more clear. So it's a function that takes in the policy pi t that you played and the observation OT that you received. And corresponding to different pi's, you can get a different number in 0 and 1. So for example, if you go back to the bandit, one way to okay, this G would not be the solution to the min-max problem, but like the corresponding G that you get from the inverse propensity weighting in EXP3 is this indicator that pi is equal to pi t and times OT.
In that setting, do you know what the solution to a min-max problem would be? How different it is?
No, I don't know. No, sorry.
Sorry?
Like this algorithm is probably not implementable for like beyond bandits when you have we have not put a lot of effort on like trying to see when or like what's the running time for this algorithm for like non-trivial problems.
So I have a more general question, I guess. So you have these observations and it's not necessarily the reward, right? So can you deal with sort of POM-DP settings in this? Like you have an observation, but it's like not super informative. Does that work? Or what assumptions? Or are there any assumptions on the observations? How does that?
Complex story. So on the upper bound side, yes. And on the lower bound side, no.
Okay.
And there is some follow-up work led by Noah Golovich, where they try to think more about POMDPs and relate POMDPs to games.
Mhm.
So that could be interesting to look at. But in this work, the lower bound requires that OT contains FT.
So, sorry, OT contains FT.
The reward, sorry, RT.
OT contains the reward. Okay, I see.
Yeah, OT
That's
contains
the lower
reward.
bound. I see.
Yes. And one other connection regarding POMDP is, if you look at the intuition for the lower bound, essentially, like, the lower bound comes from this by considering these mixture models over the model class.
Mhm.
And this is the class of POMDP that people have looked at, where, for example, you have a mixture over tabular MDPs, and you don't know the mixture, and every time when you start an episode, a fresh MDP is sampled from the mixture, and so on.
So does that mean the lower bound does apply? No.
No, the lower bound invokes the lower bound for the stochastic setting as a black box, and I think that one also
Yes,
requires you to
Okay,
know
I see.
the rewards. Yeah. But I was just making this connection that, like how
Yeah,
some
yeah,
POMDP settings are naturally
the
captured
mixture
by
model that makes sense.
this idea of convex segregation. Yes.
Okay, thank you again. Maybe we can stop the recording.
Yeah, thanks.